Hey everyone, back to a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we're going to start with a series of 4 videos about applications of Gauss Law. First of all, we'll understand what are the symmetric sources that we have and how to use them so that we can simplify our problem. Then we will understand what the general methodology is, and after that we will start an example about planar symmetry with an infinite thin sheet. So let's start! Alright, imagine we have a source over here, which is going to be, and we're going to have a surface. We call Gauss law, it's
E times the vector of the surface, the normal vector times dA over the surface, let's call it S. And it's equal to the flux, which is equal to Q over epsilon. So
this is really Gauss law, or this part and this one. What we are going to do today is to find some sources of symmetry that allow us to take this E, this electric field, out of the integral, because it's always constant along dA. So we're going to have 3 different sources of symmetry. First of all, spherical symmetry. If we have a spherical source over here, we're going to use a spherical Gaussian surface. And we can see that in this case, the electric field is going to point always parallel to the normal vector, and it's also going to have, for same radius, it's going to have the same strength. Therefore, this Gaussian surface will be very useful and will help us solve this integral very easily. Then the second source of symmetry is going to be cylindrical symmetry. If we have an infinite cylinder, so that we don't have to worry about the edge effects, we're going to have a constant electric field in the radial direction over here. And it's also going to point out of the board and into the board. Therefore, what we are going to use in these cases, it's going to be a cylindrical Gaussian surface.
it's going to go over here, it's going to go completely blind, and over here, and same over here.
In that way, there's not going to be any electric field perpendicular to these two surfaces, or we are going to have electric field pointing perpendicular to this surface over here, the cylindrical part. And the last source of symmetry, and the one that we are going to explore today, is planar symmetry. We will find that when we have an infinite plane of charge. We will see that this is going to provide us with a uniform electric field in both directions. In these cases, what we are going to do is to use some surfaces. It could be a cylinder or a cube. Probably a cylinder is better. That are going to point in this direction. In that way, the cylindrical part is not going to have any contribution to the flux, and both sides, the top and the bottom, are going to contribute to the flux. And again, we're going to be able to solve the integral much more easily. Great! Now let's try to understand the general methodology for applying Gauss law. First of all, the first step we have to do is to identify the symmetries of the system. Now that we know that, we need to define different regions depending on the charge density. After that, you need to determine, or really you need to do steps 2 and 3 at the same time. You need to determine the direction of the electric field. Now, for each of these regions, you need to do some steps. First of all, you need to define a Gaussian surface such that the flux is zero or the electric field is constant along it. After that, you need to calculate the flux through each of those sides in terms of E. Then you need to find the charge inside of each of those regions. And finally, you just need to equate both sides and solve for the electric field. And these are the general steps to apply Gauss Law in different situations. Great, let's explore, as we said, the case of a thin sheet. First of all, we will start with 1. As I said before, there's this intuition that this infinite plane, because it extends infinitely in those directions and also perpendicular to the whiteboard, it's going to create a uniform electric field all throughout space. How does that work? So if we take these two, one over here, a small element dq1 and a small element dq2, we see they are going to create an electric field in this direction and in this direction. So if we are aiming to see what happens at the middle point, we're going to have two electric fields, E1 and E2, and if we add them, we're going to have an electric field. So there's this notion that when we get closer to the surface, we're going to have a bigger electric field because we are closer to it, and therefore the charge that is over here and the closer ones are going to give a more strong electric field, much more stronger. But all the other infinite sheet is going to be very little contribution because the angle is going to be very small and it's going to cancel by pairs for the most part. And when we get farther apart from the sheet, this electric field stays constant because while this part contributes a little bit less, every electric field is a little bit weaker, there is less cancellation. The angle becomes larger and therefore, as you see, not that much part of the different contributions cancels. And that effect counters each other in the exact manner so that the electric field all throughout space for a infinite thin sheet is totally uniform. You also need to take into account, if you want to do the calculations, which is not that hard, this dimension that goes orthogonal to the whiteboard. Now we'll apply Gauss Law to prove that this is the case in a much more simple manner instead of calculating extra electric fields. But it's good to have an intuition of why this happens. If we have, once again, our thin sheet over here, with, recall from before, this is going to be our superficial charge density. Sorry about that, it's not going to be a d omega, it's going to be an omega. The omega is what these different charges is going to have. Now we're going to define our Gaussian surface, and I'll draw it in green. We're going to do a cylinder this time, but we could do a box or whatever. And we know we're going to have an electric field over here and an electric field over here, pointing in the opposite directions. And we're going to have n hat and n hat of the surface. Let's call it n hat 1, n hat 2, and this is E1, E2. Alright, now when we add the flux, we see that this integral we had before, E dot n hat dA, we can divide it really in three parts: a contribution from this surface, a contribution from this surface, and a contribution from the surface, the cylindrical surface, that is going to be zero because it's parallel to the electric field. Therefore, we're going to have this is equal to the flux over here, which is E1 times n hat 1. So E1 and the area, which if we define this to be R in both sides, a constant cylinder, we're going to have E1 by R squared plus E2 times n hat 2, it's going to be positive once again, and once again the area. So it's E2 times pi R squared. If we define this distance to be equal, let's call it D, on both sides, we know that the intensity of these two electric fields is going to be the same. So we can simply write 2 pi R squared times E. Now, what's the other part of Gauss law? It's charge enclosed over epsilon naught. So the charge enclosed in this surface, in this Gaussian surface, is going to be equal to the charge density times the area of the thin sheet that we enclose, and that is no other thing than pi R squared over epsilon naught. And this is going to be equal to the flux, which we calculated it to be 2 pi R squared times E. Now we can do some cancellations, pi R squared and pi R squared, and we find that E it's equal to epsilon naught sigma, the charge density, times 2 epsilon naught. To make this a vectorial quantity, we just need to define the two different regions in which we are working. This is going to be very useful using Gauss law. We're going to have region 1 over here and region 2. So we're going to have E in region 1, denoted by that. It's going to be a vectorial quantity, and we see it's going to be pointing to the minus I hat direction. Let's define our unit vectors. So it's minus epsilon to, sigma. I keep confusing epsilon and sigma. Epsilon naught times I hat. And in the second section, it's going to be equal to sigma over 2 epsilon naught I hat. And this is going to be the electric field generated by a uniform thin sheet. And we see it's really constant all throughout the space. That is all for today. I hope that you understood everything and got a sense on how to apply Gauss law, how to use those sources of symmetry to your advantage, and the general methodology in different cases. In the next video, we will explore planar symmetry with some examples, and things will become much more clearer. Any doubts left, you may ask them in the comment section, and remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!